Strategic cost selection in participatory budgeting explores the tactical behavior of project proposers in approval-based participatory budgeting, where they aim to set the highest possible project prices while ensuring their projects are selected and prices are not below the minimum delivery costs. In this context, the study examines the existence of pure Nash equilibria in games with fixed and known votes, focusing on the AV, cost, Phragmén, and method of equal shares rules. Participatory budgeting is a process where citizens propose projects, and funding decisions are made through voting. In this scenario, three activist groups: cycling infrastructure, city greening, and senior citizens' quality of life each submit a single project with varying cost options to improve their chosen area. The groups must strategically decide on the project cost, considering the voting rule used and the level of support for their cause. The level of support is assessed through a survey, which reveals the largest vote share for the biking enthusiasts, followed by the ecology and seniors-oriented projects. The choice of project cost depends on the voting rule. Under the basic AV rule, which selects projects with the largest number of approvals, the biking enthusiasts could propose their most expensive project. In contrast, other voting rules might favor more frugal proposals. This study sets the stage for further investigation into the existence of pure Nash equilibria and the experimental study of strategic cost selection using real-life participatory budgeting election data, providing insights into the strategic behavior of project proposers and the impact of voting rules on project cost selection. This research paper explores strategic cost selection in participatory budgeting through a game-theoretic analysis, examining the interactions between project proposers and voters. The study focuses on understanding how different budgeting rules, basic AV, cost, Phragmén, and MES influence the cost selection process. In this game, each project is controlled by a distinct proposer who strategically chooses its cost to maximize it while ensuring the project selection. The costs of selected projects, minus their delivery costs, serve as payoffs for the proposers. The paper presents a simplified model of reality, with assumptions including a fixed set of projects, common knowledge of votes, and no influence of project costs on voter approvals. These assumptions are crucial for maintaining the clarity and simplicity of the model, allowing for a baseline understanding of strategic cost selection in participatory budgeting. However, the authors acknowledge that relaxing these assumptions could lead to more general classes of games, which would require additional techniques and solution concepts from coalitional game theory or modeling uncertainty of information. The study initiates an exploration of strategic cost selection in participatory budgeting, providing insights into the strategic interactions between project proposers and voters under various budgeting rules. By examining pure Nash equilibria in these games, the paper aims to identify whether such equilibria exist and what costs are reported under these equilibria. This analysis contributes to the broader field of market analysis and game theory, shedding light on the complex dynamics at play in participatory budgeting processes. In participatory budgeting, project proposers' strategic behavior is crucial. This study delves into the analysis of a new class of cost games and the existence of pure Nash equilibria under various participatory budgeting rules and types of votes. The authors examine different scenarios, including plurality votes, party list votes, and unrestricted votes, as well as different delivery costs, such as zero and arbitrary costs. The impact of tie-breaking orders on the existence of equilibria is also explored. A participatory budgeting instance is defined as a tuple consisting of a set of projects, a set of voters, an available budget, and a cost function specifying the cost of each project. Each voter casts a non-empty approval ballot, and the approval score of a project is the number of voters who approve it. This notation is extended to define the approval score of a subset of projects. Several participatory budgeting rules are defined, including basic AV, cost, and Phragmén. Basic AV selects projects based on their approval scores, breaking ties using a predefined order. AV, cost is similar, but considers the approval-to-cost ratio of each project. Phragmén simulates a process where voters earn money at a constant rate and use it to purchase approved projects. The authors note that tie-breaking can have a significant influence on the outcome of participatory budgeting rules, but expect ties to be rare in large instances. Their rules are resolute, meaning they always produce a unique outcome. This study provides a comprehensive analysis of the strategic behavior of project proposers in participatory budgeting, shedding light on the existence of pure Nash equilibria under various rules and scenarios. Participatory budgeting, PB, is a democratic process that allows citizens to decide how a portion of public funds are spent. This paper discusses two variants of the method of equal shares, MES, designed to allocate funds to projects based on voter approval and budget constraints. The first variant, MES cost, assigns an affordability coefficient to each project, representing the fraction of its cost that voters can afford. This coefficient is calculated as the smallest number that ensures the total amount of money allocated to a project does not exceed its cost. If no such value exists, the project is considered unaffordable and removed from consideration. The rule terminates when all projects are either funded or deemed unaffordable, and it outputs the set of funded projects. The second variant, MES with approval utilities, MES April, operates similarly but replaces the cost-based affordability coefficient with an approval-based one. Here, the affordability coefficient represents the maximum amount of money a voter is willing to spend on a project, rather than the fraction of the project's cost. This allows for higher coefficients than in MES cost. Both MES variants may produce sets of projects that can be extended without exceeding the budget. To address this, the authors use Phragmén completion, which involves initiating a new Phragmén algorithm with the remaining funds and extending the output set accordingly. This defines the MES cost, PH and MES April, PH rules. The paper also discusses other PB rules, such as basic AV, which is commonly used in practice, and MES cost, which has been employed by several cities. It highlights the importance of considering special approval profiles, including plurality profiles where each voter approves exactly one project, and party list profiles where projects are grouped into parties, and each voter approves all projects from a single party. These profiles are either required in certain cities or theoretically interesting. Participatory budgeting cost games, or PB games, are defined as a tuple, P, V, B, D, where P is a set of projects, V is a collection of voters with approval preferences, B represents the budget, and D denotes the cost function. In this framework, voters approve a subset of projects, and the goal is to allocate the budget to maximize voter satisfaction. The cost function D maps each project to a non-negative cost, and the budget constraint requires the total cost of the selected projects not to exceed B. A key challenge in PB games is to design efficient algorithms that can find a near-optimal allocation of the budget. The paper proposes a novel algorithm, called the Iterative Project Elimination (IPE) algorithm, which iteratively eliminates the most expensive projects until the budget is exhausted. The IPE algorithm is shown to achieve a strong price of anarchy, which is a measure of the efficiency of the algorithm in achieving the optimal allocation. The authors also introduce a new concept, called the cost gap, which measures the difference between the total cost of the projects approved by the voters and the budget. The cost gap is used to analyze the performance of the IPE algorithm and to provide tighter bounds on the price of anarchy. The paper presents a comprehensive evaluation of the IPE algorithm through experiments on real-world datasets, demonstrating its effectiveness in finding near-optimal solutions. The results also highlight the importance of considering the cost gap in the design of algorithms for PB games. In the context of participatory budgeting, PB games, the existence of Nash equilibria is examined, with a focus on various cost functions and tie-breaking orders. A comprehensive table summarizes the findings, revealing the presence or absence of Nash equilibria under different cost functions and tie-breaking orders. A novel concept, the approval proportional strategy profile, is introduced as a natural solution for rules prioritizing proportionality under plurality protocols. This strategy profile is characterized by its ability to allocate budgets proportionally, based on the approval votes received by each project. The analysis explores the interplay between cost functions and tie-breaking orders, demonstrating that the existence of Nash equilibria is highly dependent on these factors. Specifically, it is shown that under certain cost functions, such as the utilitarian and egalitarian models, Nash equilibria are guaranteed to exist, whereas others, like the proportional and majoritarian models, do not always admit a Nash equilibrium. The paper's findings have significant implications for the design of participatory budgeting mechanisms, highlighting the importance of carefully selecting cost functions and tie-breaking orders to ensure the existence of stable outcomes. Furthermore, the approval proportional strategy profile offers a promising approach for achieving proportionality in PB games, providing a valuable contribution to the ongoing development of fair and efficient budget allocation methods. The limitations of basic AV are addressed through the introduction of AV cost, which implements an approval proportional strategy as an equilibrium. This approach is characterized by three key propositions. Firstly, when delivery costs are limited, all projects are funded using the entire budget. Secondly, AV cost funds all projects if delivery costs are limited. Thirdly, for any given PB game and A/D tie-breaking order, an AV cost Nash equilibrium (NA) can be computed in polynomial time. The authors provide an illustrative example, example 2, to demonstrate the complexity of AV cost. This example highlights that even with plurality-based scoring rules, AV cost can exhibit intricate behavior. The approval proportional strategy in AV cost ensures that projects are funded in proportion to their approval rates, thereby alleviating the shortcomings of basic AV. The polynomial time computability of AV cost NA is a significant finding, as it enables efficient calculation of the equilibrium. This, in turn, facilitates the practical implementation of AV cost in real-world applications. The author's work contributes to the development of more effective and efficient project funding mechanisms, addressing the limitations of existing methods like basic AV. Overall, AV cost offers a promising approach to project funding, characterized by its approval proportional strategy and polynomial time computability. Its ability to fund all projects when delivery costs are limited and its efficiency in computing the NA make it a valuable contribution to the field. Phragmén is a voting rule that can be analyzed in the context of participatory budgeting games. In the case of plurality ballots, Phragmén is identical to the AV cost rule. This means that the results from the previous section can be translated to Phragmén. Specifically, Corollary 1 states that for each PB game with plurality ballots, if the demand of each project is less than or equal to the approval proportion of the project, then the approval proportion is the only Phragmén equilibrium, NA, for every tie-breaking order. However, for an A/D tie-breaking order, there is a Phragmén, but there are games and tie-breaking orders with no Phragmén. Proposition 4 also holds for Phragmén, indicating that there are games with equilibria where Phragmén funds projects whose total cost is an arbitrarily small fraction of the budget. For party list ballots and zero delivery costs, Proposition 5 shows that there is a unique Phragmén, where each project's cost is proportional to the number of its approvals divided by the size of its party. The cost for each project can be computed as C, P, equals B, A, P, V, party, P, where B is the budget, A, P, is the set of voters approving project P, V is the set of voters, and party, P, is the party of project pages. However, for party list ballots, the cost computation is more complex due to the presence of multiple projects per party. In participatory budgeting games, the existence and computability of Nash equilibrium profiles are crucial. Theorem 2 establishes that for every PB game, a polynomial time computable Mies cost NA profile exists, unique up to the actions of unselected projects by MES cost. This is proven by identifying the project with the most approvals and showing it can always request the full amount of money from its voters. In contrast, the Mies April mechanism is more complex due to the possibility of non-existence of an equilibrium, even for a party list profile with only 3 projects and 1 voter. However, Theorem 3 shows that for every PB game with plurality ballots, a polynomial time computable Mies April NE exists, regardless of the internal tie-breaking order and delivery costs. Similarly, Theorem 4 states that for every PB game with party list ballots and zero delivery costs, a polynomial time computable Mies April NE exists, regardless of the internal tie-breaking order. Example 3 illustrates a scenario with 3 projects and 1 voter where Mies April NE does not exist due to delivery costs and tie-breaking order. Conversely, Theorem 5 demonstrates that for a party list instance, an internal tie-breaking order and corresponding Mies April NE can be efficiently computed. However, Proposition 7 provides a counterexample, showing that there are games with zero delivery costs for which no mise April NE exists, regardless of the tie-breaking order. The authors highlight the differences between mise April and Phragmén mechanisms, including the existence of NE and obtained equilibria. Notably, Theorem 6 reveals that in some instances, symmetric projects submit different costs in a mise April NE. The authors conduct an experimental analysis of their game-theoretic models using real-life participatory budgeting (PB) instances from Pabulib. 2 instances are examined. One from Wesela, Poland, and one from Kleine Wereld, Netherlands. These instances are characterized by their number of projects, voters, budget, and voting rule used in the original election, as outlined in Table 2. In the first experiment, the authors compute the best response for each project, defined as the highest cost that would still result in funding under the given PB rule. The winning and losing margins are then calculated as the difference between the best response and the original cost. Figure 2 illustrates the winning and losing margins for all projects in the 2 instances under different PB rules. The results show that under basic AV, projects with the most approvals have high winning margins, while the remaining projects have zero best responses. In contrast, under AV, cost, Phragmén, and mise April, pH, the best responses roughly correspond to the number of approvals each project received. The primary observation is that unless a project received relatively few approvals, its proposers could have reported a much higher cost without affecting funding, suggesting that proposers should choose reasonable project costs rather than minimizing them. In the second experiment, the authors aimed to compute approximate equilibria for the 2 instances under different PB rules. While equilibria can be computed directly for basic AV, cost, and MES cost, pH, dynamic simulations are used for Phragmén and mise April, pH. Although the results of these experiments are not presented, the authors note that the chosen instances are particularly illustrative, and similar conclusions can be drawn from analyzing other instances from Pabulib, as shown in Appendix B. In the context of participatory budgeting, researchers have long sought to understand the dynamics of resource allocation and their relationship with Nash equilibrium. To this end, a game-theoretic model is proposed, wherein each proposer is treated as an agent aiming to maximize their utility by adjusting the cost of their project. The game is defined such that each agent has a strategy set consisting of possible cost adjustments, with the objective being to minimize the difference between the cost and the budget allocated. A specific dynamics rule is introduced for updating the cost of each project, involving the random selection of a proposer and adjusting their project's cost based on whether it was winning or losing in the previous iteration. This process is repeated for 10,000 iterations to observe convergence towards a Nash equilibrium, if one exists. The outcomes of these dynamics are illustrated under different allocation rules, including basic AV, cost, Phragmén, mise April, pH, and MES cost, pH. Notably, under basic AV, the entire budget is allocated to the project with the highest number of votes, while under AV, cost, each project's cost becomes proportional to its support. Phragmén and mise April, pH produce similar results, whereas MES cost, pH exhibits distinct outcomes. A key limitation of this analysis is the potential lack of a Nash equilibrium in certain scenarios, particularly for Phragmén and mise April, pH. Although a direct method to verify the existence of an equilibrium is lacking, the results suggest that the observed profiles are close to being equilibria. This study contributes significantly to our understanding of participatory budgeting mechanisms and their potential for achieving efficient allocations in the context of public goods provision. By employing game theory and simulation techniques, the authors provide valuable insights into how different allocation rules influence the distribution of resources and the emergence of Nash equilibria. These findings have important implications for policymakers and researchers seeking to improve the effectiveness of participatory budgeting processes. Figure 3 illustrates the strategy profiles after 10,000 iterations of the proposed dynamics, showcasing the final costs of winning and losing projects under various rules. The green bars represent the final costs of winning projects, with the brighter portion highlighting the increase compared to the original cost. Red bars indicate the final costs of losing projects, while black outlines denote the original costs of the projects. Black triangles mark the originally winning projects, and brown circles represent the equilibrium costs for rules where they can be computed. A key observation from this experiment, supported by simulations for other PB instances in Appendix B, is that under AV, cost, Phragmén, and Mies-April, pH rules, proposers are incentivized to use costs that closely reflect the number of approvals they receive. In contrast, under MES cost, pH, strongly supported projects and those backed by many voters who do not approve other popular projects can request significantly higher costs. This leads to an equilibrium where MES cost, pH funds fewer, more expensive projects compared to AV, cost, Phragmén, and Mies-April, pH. This finding is crucial, suggesting that MES cost, pH may be preferred in practice, as funding only cheap projects can be logistically problematic for cities, requiring significant effort in coordinating their implementation. Notably, the presence of red bars in Figure 3 indicates that the equilibrium was not reached within 10,000 iterations, as all projects should be winning in an equilibrium scenario. The researchers have developed a game-theoretic framework for strategic cost selection in participatory budgeting scenarios, focusing on 4 rules: basic AV, cost, Phragmén, and MES. They investigated the conditions for the existence of Nash equilibria in these games and analyzed the effects of iterative, profitable changes in project costs using real-life election data. This framework is believed to lay the groundwork for further theoretical and experimental studies. Future research directions include establishing the complexity of deciding if equilibria exist in these games and studying a more involved class of games emerging from relaxing the basic assumptions. The authors are interested in verifying whether increased model complexity leads to new dynamics or reinforces observed phenomena. The authors acknowledge funding from the European Research Council under the European Union's Horizon 2020 Research and Innovation Programme and additional support from the European Union for Peter Skowron. This video delves into the multifaceted realm of multi-winner voting, participatory budgeting, and social choice theory. These fields are interwoven by their shared goal: to devise systems that efficiently aggregate individual preferences into collective decisions. Multi-winner voting, as the name suggests, involves electing multiple candidates or options simultaneously. It is often used in political elections where multiple seats are up for grabs, but also applies to other contexts such as choosing products for a limited time promotion. In this context, researchers have developed various algorithms to ensure fair representation and satisfaction among voters. For instance, proportional representation methods aim to allocate seats proportionally to the number of votes received, while non-proportional methods prioritize the most popular candidates. Participatory budgeting, on the other hand, is a democratic process in which community members decide how a portion of a public budget will be spent. This approach has been increasingly adopted worldwide as it fosters citizen engagement and ensures that public funds are allocated according to community needs and priorities. Studies have shown that participatory budgeting can lead to more equitable distribution of resources and better alignment with community needs. Social choice theory, meanwhile, is an interdisciplinary field that studies how individual preferences are aggregated to reach a collective decision. This theory underpins both multi-winner voting and participatory budgeting, as well as many other decision-making processes. Researchers in this field explore various voting rules, their properties, and how they can be manipulated or gamed by strategic voters. A significant challenge in these fields is dealing with Arrow's impossibility theorem, which states that no voting system can satisfy all of a set of reasonable-sounding criteria simultaneously. This has led researchers to develop compromise solutions that balance competing objectives, such as fairness, efficiency, and strategic stability. In conclusion, this video provides an overview of the complex and interconnected fields of multi-winner voting, participatory budgeting, and social choice theory. These areas of research aim to develop fair, efficient, and engaging systems for collective decision-making, despite the challenges posed by Arrow's impossibility theorem. Page 15 of the research paper presents the proofs of 3 propositions related to the concept of Nash equilibrium, NE, in the context of project-based games, PB games, and the approval vote, cost, AV, cost, mechanism. The first proposition demonstrates that a strategy profile C is a basic AVNE if and only if the project P, such that C, P, equals B, is not selected when its cost is decreased or increased. This result has implications for the strategic behavior of projects in PB games. The second proposition shows that in a PB game, if the total reported cost is less than or equal to the budget B, then the AV cost mechanism selects all projects. However, if the total reported cost is greater than B, there exists a project P in the set of funded projects P1 such that C, P, greater than AP, P, is greater than or equal to D, P. This leads to a contradiction, implying that the total reported cost must be equal to B. This finding highlights the importance of budget constraints in PB games. The third proposition demonstrates that in a PB game where the domain constraint D, P, is less than or equal to AP, P, holds for every project P, the strategy profile C equals AP is an AV cost NE. Any other strategy profile C other than AP is not an AV cost NE. This is achieved by assuming that a project P can report a higher cost key and still be selected by AV cost, obtaining a better payoff. These proofs rely on rigorous mathematical arguments, utilizing concepts such as utility functions, cost reports, and approval proportional profiles. The results have significant implications for the design of mechanisms in PB games, emphasizing the importance of considering the strategic behavior of projects in the AV cost mechanism. Algorithm 1, presented in the research paper, is designed to find a Nash equilibrium for the approval voting with costs, AV cost, game. The input data includes a set of projects P with their delivery costs function D, a set of voters V with their ballots, a budget B, and an approval, delivery, A, D, tie-breaking succeeds. The algorithm outputs a profile C that is an AV cost Nash equilibrium, NE, under the given tie-breaking. The algorithm initializes the remaining budget B to B and sets the initial strategy C to the delivery costs of the projects. It then iteratively selects a group of prospective projects PP and updates the costs of these projects based on their approval-to-delivery cost ratios. This selection process is guided by the tie-breaking succeeds, which orders the projects non-decreasingly according to their ratios. In each iteration, the algorithm finds the maximum integer x such that the total approval of the top x projects does not exceed the remaining budget B. The algorithm then updates the costs of the top x projects and removes them from the set of prospective projects. This process continues until all projects have been considered or the remaining budget is depleted. The proof of Theorem 1 is also provided, showing that algorithm 1 computes the claimed AV cost NE. The proof introduces helpful notation and discusses the tie-breaking succeeds in more detail. It demonstrates that algorithm 1 finds a Nash equilibrium by iteratively selecting projects that underreport their costs compared to the support they receive. The correctness of the algorithm is proved using claim 1, which states that in any Nash equilibrium, all projects are selected to be funded. In decentralized funding mechanisms, optimizing fund allocation to projects is crucial. To achieve this, algorithm 1 ensures that the entire budget is utilized and prevents single projects from manipulating the system by underreporting their costs. The algorithm operates on a set of projects, P, ordered by their cost-to-approval ratio. It iteratively updates project costs until the budget is exhausted or no projects underreport their costs. Key components of the algorithm include identifying top projects in P, calculating the cost-to-approval ratio T, and adjusting project costs to prevent underreporting. The algorithm's output profile, C, generated by algorithm 1, exhibits specific properties. After each iteration, the following conditions hold. All projects in top, K, are funded under strategy profile C. There exists a project P that is not funded and has no profitable deviation for C. No project in top, K, has a profitable deviation for any strategy profile C, differing from C only by strategies of projects in PP, and no project in PP has a profitable deviation in C. The proof of these properties involves an inductive argument over the while loop iterations, demonstrating that the algorithm correctly identifies and adjusts project costs to prevent underreporting and ensure full budget utilization. The algorithm terminates when PP becomes empty, indicating that all projects have been considered and the budget is fully utilized, resulting in a Nash equilibrium. In this section, the authors delve into the analysis of a novel mechanism for allocating funds to projects, with a focus on the concept of strategy-proofness. The game-theoretic model presented here involves players as projects competing for a budget, where their ultimate goal is to maximize their probability of being funded. A strategy-proof mechanism is defined as one that ensures no project can increase its chances of approval by misrepresenting its cost. The paper then proceeds to prove the strategy-proofness of a specific mechanism, which utilizes a modified version of the Vickrey-Clark-Groves (VCG) mechanism. The VCG mechanism is renowned in game theory for its ability to induce truth-telling behavior in bidders. In this context, the authors modify the VCG mechanism to accommodate the constraints of the project allocation problem. The main result of this section is the proof of two key properties of the proposed mechanism. Firstly, they show that the mechanism is strategy-proof for any number of projects, meaning that no project can benefit from misrepresenting its cost. Secondly, they demonstrate that the mechanism is budget-balanced, ensuring that the total cost of funded projects does not exceed the available budget. To achieve these results, the authors employ a series of logical arguments and mathematical proofs. They consider different scenarios based on the number of projects and their reported costs, and use these scenarios to establish the desired properties of the mechanism. The analysis involves detailed calculations involving the cost-to-approval ratio, which plays a crucial role in determining the order in which projects are considered for funding. Overall, this section contributes to the development of a novel mechanism for allocating funds to projects in a strategy-proof manner, ensuring that all projects report their true costs and maximizing the overall efficiency of the allocation process. The authors provide a rigorous proof for the correctness of Algorithm 1 and Theorem 1, as well as Proposition 4, which establishes the existence of a Phragmén-Nash equilibrium strategy profile in a project-based game, or PB game. To prove the correctness of Algorithm 1, the authors first establish Claim 1, which ensures that the algorithm's decision-making process is optimal and no project can benefit from changing its strategy under the given cost function C. This is achieved through mathematical induction, starting with the base case and extending the argument to the xth iteration of the while loop in Algorithm 1. In the base case, the authors demonstrate that the algorithm's initial state PP has no profitable deviation for any project. They categorize projects into those removed in the for each loop, the project P** operator, and those removed in line 16, and prove that none of these projects have a profitable deviation. For the induction step, the authors assume that the base case claims hold for the x1th iteration and then extend their argument to the xth iteration, using the same categorization approach to prove that no project can benefit from changing its strategy under the cost function C. The authors also provide a proof for Proposition 4, which demonstrates the existence of a PB game with a Phragmén-Nash equilibrium strategy profile. They construct a game with 3 projects and a specific voter preference profile, illustrating the feasibility of such an equilibrium. This novel result has significant implications for the study of project-based games and their strategic behavior. In this section, the authors provide a proof for Proposition 4, which states that the strategy profile C defined in the statement of the proposition is a Phragmén-Nash equilibrium, NA. This proof involves demonstrating that no player can unilaterally improve their payoff by changing their strategy, while keeping all other players' strategies constant. This is achieved through a series of logical deductions and mathematical calculations, utilizing the properties of the Phragmén rule and the given budget constraints. Following this, the authors proceed to prove Proposition 5, which asserts that the strategy profile C is the unique Phragmén NE for the considered PB game G. This proof involves showing that any arbitrary equilibrium C must satisfy certain properties, such as all projects being funded under C, and all projects within a party reporting the same cost. By leveraging these properties, the authors demonstrate that C must be identical to C, thus establishing the uniqueness of the Phragmén NE. Finally, the authors present a proof for Proposition 6, which claims that there are no Nash equilibria for a specific PB game G. To prove this, they assume the existence of a Phragmén NE C and then derive a contradiction by analyzing the time moments when voters would collect money from the projects they approve. Through this analysis, they demonstrate that all projects in P must be funded under C, and that this leads to a contradiction, thereby proving the non-existence of Nash equilibria for the given game. The authors present a detailed analysis of the PB game, as illustrated in Figure 4, which is used to prove Proposition 6. This game consists of 6 projects, denoted by P and P, with their corresponding voters, V. The projects are represented as boxes, and each voter approves projects drawn directly above them, indicated by a dotted line. The authors establish several key properties of the game, including the equalities. Time, P1, equals time. P2, time. P3, equals time. P1, equals time. P2, and time. P1, equals time. P2, equals time. P3. These equalities lead to the definitions of time, and time. Where time, equals time. P1, equals time. P2, equals time. P3, and time, equals time. P1, equals time. P2, equals time. P3. Consequently, C, P1, equals C, P2, equals time, C, P1, equals C, P2, equals time, C, P3, equals 3 time, and C, P3, equals 3 time. The authors then demonstrate that time equals time by considering 2 cases. Case A, where at least one of P1 and P2 is preferred to P3 by the tie-breaking order, and Case B, where P3 is preferred by tie-breaking to both P1 and P2. In each case, they show that if time less than time, then it is beneficial for a project to slightly increase its cost, leading to a contradiction with the equilibrium condition. The symmetric case, where time less than time, is also considered. This analysis provides a detailed understanding of the strategic interactions between projects and voters in the PB game, and sets the stage for further results in the paper. In the context of a minimum expenditure surplus, MES, cost proportional budgeting, PB, game, we demonstrate the non-existence of a Nash equilibrium under Phragbmén's method. Assuming a hypothetical Nash equilibrium C** operator, we derive contradictions, thereby proving its non-existence. The proof proceeds through 2 cases. A and B. In case A, we assume P3 precedes both P1 and P2 in the tie-breaking order, and P3 precedes both P1 and P2. This assumption ensures that if P3 were not first in the tie-breaking order, P1 and P2 would be funded before P3, leading to a contradiction, as voters in V would have more money than those in V. In case B, we assume at least one of P1 and P2 is preferred to P3 due to tie-breaking at time. Consequently, both P1 and P2 are funded at time, leaving only projects P3 and P3 unselected. Since voters in V have more money than those in V, if P3 increases its cost to be slightly below that of P3, it will be funded before P3, again leading to a contradiction. In both cases, the assumption of a Nash equilibrium C** operator leads to contradictions, thereby proving that no Nash equilibrium exists under Phragbmén's method in a MES cost PB game. Furthermore, we outline an iterative algorithm for computing the strategy C in a MES cost PB game. This algorithm iteratively removes projects from consideration based on their demand and budget constraints, updates the strategy C for each project, and identifies the project with the minimum alpha j value for further consideration. The algorithm for the mechanism for election strategy with cost, MES cost, is outlined, which iteratively selects projects and removes their supporters from the set of voters. The strategy for each project is determined by dividing the total budget of its supporters by the total number of voters. Claim 2 is introduced, stating that for each alpha affordable project, alpha equals 1 over the number of voters who approve the project and have a non-zero budget. This claim is utilized to demonstrate that in each Nash equilibrium, MES cost selects projects in a specific order and reports their costs accordingly. The proof of Theorem 3 is provided, illustrating that in a MES-April PB game with plurality ballots, each project reports its cost as the minimum of its delivery cost and the maximum amount it can request from its supporters. The proof of Theorem 4 is also presented, showing that in a Mies-April PB game with party list ballots and zero delivery costs, each project reports its cost as the minimum of its delivery cost and the total budget of its supporters. The mechanism is proven to select projects in a specific order, with each project reporting a cost equal to the total budget of its supporters divided by the total number of voters. This selection process is demonstrated to be a Nash equilibrium, highlighting the efficiency and stability of the MES cost algorithm in the context of participatory budgeting games. In the context of party list ballots, the cost revelation game Mies-April orders projects within parties based on their delivery costs and tie-breaking orders. A Nash equilibrium in this game, denoted as Mies-April NE, is a crucial concept. However, not all cost profiles lead to a Mies-April NE, as illustrated by an example in the paper. Theorem 5, meanwhile, establishes that under certain conditions, a Mies-April NE exists. The proof begins by defining the total money available to supporters of a party, M, party, pi, and the alpha value of a project, which is determined by its delivery cost and the number of supporters in its party. Mies-April orders projects from the cheapest to the most expensive, following the specified tie-breaking order in case of a tie, and equally distributes the budget from the party supporters to fund the next project unless the cost exceeds the money available. There are two cases to consider for the last project in the tie-breaking order within a party. If the delivery cost does not exceed the money available to the party's supporters, each project submits its cost as M. Party, pi, gets funded, and no project benefits from changing its cost. This mirrors the scenario in Theorem 4, where an equilibrium exists due to the equal distribution of the budget among projects. The paper highlights the importance of considering both the cost revelation game and the Nash equilibrium in the context of party list ballots. It demonstrates that not all cost profiles lead to a Mies-April NE and provides conditions under which a Mies-April NE exists. The role of the tie-breaking order in determining the distribution of the budget among projects within a party is also emphasized. In approval voting, the creation of a Nash equilibrium in approval voting, NEAV, is intricately linked to the existence of a minimal envy-free allocation, MESA. This connection is explored through the introduction of a novel concept, MESA approval resistant, Mies-April, which refers to an allocation that prevents voters from expressing envy towards other voters. A pivotal proposition is presented, stating that when there are at least 4 projects, no Mies-April NE exists for any approval voting rule. This means that in scenarios with 4 or more projects, it is impossible to achieve a Nash equilibrium in approval voting that also satisfies the minimal envy-free allocation property. To prove this proposition, the authors construct a specific instance with 4 projects and 16 voters, where each project has 3 unique supporters and 2 shared supporters with neighboring projects. Under this setup, they demonstrate that no Mies-April NE can exist due to the constraints on project costs and voter budgets. Specifically, each project must be selected in the Mies-April NE, and the total cost of all projects must not exceed the total budget. However, this leads to a contradiction, as the minimum cost required for a project to be considered affordable according to the Mies-April rule would eventually exceed the remaining budget, thus proving the non-existence of a Mies-April NE. This result has significant implications for the design of approval voting systems, suggesting that achieving both Nash equilibrium and minimal envy-free allocation may be difficult in certain contexts. This research contributes to ongoing studies on the properties and limitations of different voting rules, highlighting the challenges in balancing individual preferences and fairness in collective decision-making processes. The authors of the research paper assume, without loss of generality, that project P1 has the lowest cost and wins ties if there are multiple projects with the same cost. They also assume that C, P2, is less than or equal to C, P3, and P2 wins ties with P3. The authors exclude cases where C cannot be Mies-April NE, specifically when there is no project with the same cost as P1. In this scenario, P1 could increase its cost by a small positive number epsilon and still be considered first, implying that C cannot be Mies-April NE. With these assumptions, project P1 is selected in the first iteration, and each of its supporters pays C, P1, 5. Voter V1 has insufficient money to contribute the equal share C, P2, 5 to purchase P2. In the second iteration, alpha 2, P4 equals C, P4, 5, alpha 2, P2 equals C, P2, BC, P1, 5, 4, and alpha 2, P3 equals C, P3, BC, P1, 5, 4 is greater than or equal to alpha 2, P2. The authors show that alpha 2, P2 greater than alpha 1, P1, implying that project P4 would regret saying the same cost as project P1. Therefore, it cannot be the case that C, P1 equals C, P4, and due to previous reasoning, C, P1 equals C, P2, and C, P1 less than C, P4. The authors considered two cases. Project P4 is selected in the second iteration, or project P2 is selected in the second iteration. In the first case, alpha 2, P4, equals alpha 2, P2, and the authors derive equations for C, P3, and C, P4, based on the amounts of money that projects P2 and P3 request from their supporters. They show that C, P1, equals 7B, 2 and C, P4, equals 4B. In the second case, alpha 2, P2, equals alpha 2, P4, and the authors demonstrate that if project P1 changes its cost from C, P1, equals 7B, 2 to C, P1, equals 36B, 10, it would get selected with a higher cost, implying that C could not be Ms. April NE. The authors delve into the mechanism for approving projects, focusing on the scenario where voters V1 and V2 select projects P1 and P2, respectively. They calculate the costs of projects P3 and P4, denoted as C, P3, and C, P4, revealing that C, P4, equals 6C, P1, minus 5B, 4. The analysis explores two cases. First, where project P3 is selected before project P4, and second, where project P4 is selected before project P3. In the first case, the supporters of project P2 have sufficient funds to purchase project P4, allowing project P1 to improve its utility by adjusting its cost. This demonstrates that the proposed mechanism is not a mixed integer second price, MES, April NE in this scenario. In the second case, even when voter V9 pays a greater share to buy project P4 and is left with less money, there is still enough funding to purchase project P3. This means project P2 can increase its cost, lose in the second iteration with project P4, yet still be funded before project P3 and acquire more money. Consequently, the proposed mechanism is not Ms. April NE in this case either. The authors conclude that no tie-breaking order exists for which Ms. April NE holds for the given instance. They then proceed to prove Theorem 6, which asserts that the constructed example is a narrowed version of the instance from Proposition 6, featuring 3 voters and 3 projects, with a specific tie-breaking order between projects. The authors extend their analysis to additional participatory budgeting, PB, instances from the 2022 elections in various Warsaw districts, including Bemowo, Bielany, Wilanów, and Wielkopolska. The characteristics of these datasets are outlined in Table 3. The winning and losing margins for these real-life PB instances are presented in Figure 6, while Figure 7 illustrates the strategy profiles after 10,000 iterations of the proposed dynamics. A comparison of the original winning and losing margins with those observed after 10,000 iterations is provided in Table 4. The results show that, in most cases, the size of the margin significantly decreases, indicating a more balanced distribution of resources among projects. To further illustrate this, the authors consider a Ms. April NE instance with 3 projects, P1, P2, P3. They demonstrate that both cost vectors C equals C, P1, equals 7B, 36, C, P2, equals 8B, 36, C, P3, equals 21B, 36, and C, equals C, P1, equals 8B, 36, C, P2, equals 7B, 36, C, P3, equals 21B, 36, are Ms. April NE for this instance. This is achieved by showing that no project benefits from lowering its costs, as it would not gain an advantage, and no project would increase its cost, as it would lose in previous iterations and its supporters would not have sufficient funds to purchase it. Table 4 compares winning and losing margins in the original elections and after 10,000 iterations of the game, across 6 districts: Bemowo, Bielany, Wesela, Wilanów, Włochy, and Klina Wereld. The table displays the average and standard deviation of winning and losing margins in 1,000 Polish zloty, or year, for 5 different rules: Basic AV, Cost, Fhragmén, Mise April, pH, and MES Cost, pH. The results show that winning margins are generally higher than losing margins, with the largest differences observed in the Bielany and Włochy districts. The Fhragmén and Mise April, pH rules tend to produce smaller winning margins and larger losing margins compared to the other rules. The MES Cost, pH rule exhibits higher variability in winning and losing margins across different districts. Notably, the standard deviations of the winning and losing margins are often substantial, indicating significant variability in the outcomes. These findings are crucial in understanding the behavior of different rules in proportional representation systems and can inform the design of electoral systems that aim to achieve fair and representative outcomes. The choice of rule can have a significant impact on the distribution of winning and losing margins in the elections, highlighting the importance of careful consideration when designing electoral systems. Figure 6 illustrates the winning and losing margins in real-life project-based (PB) auctions, providing a comprehensive understanding of bidding outcomes. The green bars represent the maximum winning cost, with the brighter portion indicating the winning margin. Conversely, the red bars depict the minimum losing cost, with the white portion illustrating the losing margin. The black outlines denote the original costs of the projects. Winning margins are calculated as the difference between the maximum winning cost and the original cost, while losing margins are computed as the difference between the original cost and the minimum losing cost. The winning and losing margins offer valuable insights into the bidding strategies employed by participants in PB auctions. Notably, the winning margins are generally higher than the losing margins, suggesting that winners tend to bid more aggressively than losers. This observation has significant implications for auction design and bidder behavior in PB auctions. The disparity between the winning and losing margins may be attributed to factors such as risk aversion, incomplete information, or strategic bidding. The author's analysis of the winning and losing margins in Figure 6 builds upon their previous findings on the bidding behavior in PB auctions. By examining the cost distributions and bidding patterns, the authors aim to identify the underlying mechanisms driving the auction outcomes. This research contributes to the understanding of PB auctions and informs the development of more efficient auction mechanisms. In the context of the broader research, Figure 6 provides empirical evidence supporting the author's claims regarding the importance of considering bidding behavior and auction design in PB auctions. The results have significant implications for policymakers, auctioneers, and bidders seeking to optimize their strategies in real-life PB auctions. The game's outcomes after 10,000 iterations are presented in Figure 7, showing the final costs of winning and losing projects. Green bars represent winning projects, with brighter portions indicating increased costs compared to their original values, black outlines. Conversely, red bars depict losing projects. Notably, black triangles mark projects from the original Pareto boundary, PB, while brown circles indicate the Nash equilibrium, NA. The figure reveals that winning projects' costs have increased, whereas losing projects' costs have decreased due to the game's dynamics, where projects adapt and adjust their costs to optimize their chances of winning. The presence of a Nash equilibrium indicates that no single project can improve its cost without affecting others, leading to a stable state. These results demonstrate the effectiveness of the proposed game-theoretic approach in modeling complex project interactions and identifying optimal cost allocation. By iteratively updating costs based on game outcomes, the approach converges to a stable equilibrium, reflecting project strategic behavior. This page builds upon previous sections introducing the game-theoretic framework and iterative cost update mechanism. The results validate the theoretical foundations of the approach, showcasing its ability to capture intricate project relationships and allocate costs efficiently. The findings imply that the proposed method can be applied to real-world project portfolio optimization problems, aiming to allocate resources and costs effectively among competing projects. The approach's ability to converge to a Nash equilibrium suggests it can handle complex, dynamic systems, making it a valuable tool for decision-makers and stakeholders. Limitations include assuming a fixed number of projects and simplifying the cost update mechanism. Future work may involve relaxing these assumptions and exploring the application of the game-theoretic approach to more realistic and complex project portfolio optimization scenarios.